Alrighty, we have a 1 liter flask that initially contains 0.298 moles of PCl3 and 8.70 times 10 to the negative 3 moles of PCl5. Equilibrium is established, and at equilibrium, 2.00 times 10 to the negative third moles of chlorine are in the flask. They would like for us to calculate the equilibrium concentrations of all the species, so everything in the chemical reaction, and the value of K. They didn't specify what kind of K, so we are going with KC. Looking at all the information in the question, I was given some initial values and an equilibrium value, and they're asking me to solve for additional equilibrium values. So anytime you have initial and equilibrium values in the same problem, this is going to be an ICE chart. So all ICE charts start with the balanced chemical equation. And then we're going to write ICE down the left-hand side. I will stand for initial. C will stand for change. E will stand for equilibrium. We're going to draw an additional row and turn this into an ICEE chart. That additional E row also stands for equilibrium. So the main difference here between our two equilibrium rows is that the first one is equilibrium in terms of X, and the second equilibrium row will be the actual molarity of the chemical species at equilibrium. All right, so I have my basic outline of my ICEE chart, and what makes this really handy is that it keeps all the information organized for me. We're going to plug in all the information that we know about this chemical system into this ICEE chart. I am given the initial concentration of PCl3. It's 0.298 moles. And so I'm going to plug that into my ICE chart. But ICE charts need to be in terms of molarity, i.e. concentration, the moles per liter. So I do need to take into consideration the volume of the flask. The volume of this flask is 1 liter. So conveniently, the number of moles is also going to be the molarity of the chemical species. So we're taking 0.298 moles of PCl3. That is also its molarity because the volume is 1. So under initial, we're going to write 0.298 molar for PCl3. And then we're also going to write down the amount of PCl5. They gave me the initial value. That's 8.70 times 10 to the negative third. And again, volume is 1 liter, so the number of moles will also be the molarity. Another value that they gave me was the equilibrium moles of the chlorine gas. And so I'm going to plug in 2 times 10 to the negative third molar chlorine, but because this is the equilibrium number of moles of chlorine, I have to put on the equilibrium row inside of my ICE chart. And we do know the actual molarity of this, so this is going to be the second E row, the very last row in my chart. Alrighty, so I have now inputted all the information from the question into my ICE chart, and now I need to solve for the equilibrium molarities of everything in this chemical system. So I need to figure out what the equilibrium concentration of PCl5 is, and what the equilibrium concentration of PCl3 is. And so I'm looking here, and I noticed that I got a bunch of blank boxes which I need to fill in. And they didn't tell me that we put any chlorine gas into the flask. The only two things that we put into the flask were the PCl5, PCl3. So it is safe to assume that the starting value of chlorine gas is going to be 0. Now for the change row. We need to know in which direction the system will proceed to establish equilibrium. Since we have 0 chlorine initially in the flask, the reverse reaction is impossible initially because we have 0 of one of our products. And so there's only one direction that this system is going to proceed, and it's going to be in that forward direction. So for that change row, I'm going to go ahead and draw an arrow. I know that this reaction is going to proceed in the forward direction. And for future problems, know that anytime you have a chemical species that starts with an initial concentration or initial partial pressure of 0, the reaction is going to proceed towards the side with the initial 0. Okay, so for the change, we know we're going forward. And this is when we're going to start to write down how much reactant is used and how much product is made. Now, we don't know exact moles or molarities, but we do know that the balance equation and their coefficients tells us that mole ratio in which the reactants are used and the products are made. And so this change row, you can really think of that C as coefficient time. You're now going to look at the coefficient of each chemical species and use it in sort of a mole ratio. The coefficient of our reactant is 1, and we know that it's being used, and so we're going to subtract some amount, and we're going to say minus 1x. For our first product, PCl3, its coefficient is 1, and since we're moving in that forward direction, we know we're making some product, and we're going to say we're going to make plus 1x. And then for the chlorine, we're also making some chlorine, and its coefficient is 1, and we're going to say plus 1x. And so what's happening here for the change row is that we are subtracting from the reactant side, and we're adding to the product side because we're moving in the forward direction. We're making product. I'm writing an x for each one because x represents some quantity. Okay. And I'm writing a 1 for each one of those as its coefficient because I'm pulling down the coefficient from the balance equation. And we're saying that for every 1 mole of PCl5, 1 mole of PCl3 is made, and 1 mole of chlorine is made. Now for our equilibrium row that's written in terms of x. This is the easiest one. You're just going to combine the I and the C together. And so we're just going to 8.70 times 10 to the negative third minus molar minus 1x. And then PCl3, 0.298 molar plus 1x. And the chlorine will be 0 plus 1x. And so that's what I mean by having an equilibrium row in terms of x. We have the combination of initial and the change with this variable of x, whatever x might be. Now comes the part where we need to solve for x. There will always be some way that we can solve for x. For an ICEE chart, the two equilibrium rows equal one another. It's just that the first row is in terms of x, and the second row is the actual concentration of that chemical species at equilibrium. And so both of these rows are equal to one another. And so I look for the one chemical species in which I have values for both of the equilibrium boxes, and that's going to be right here with that chlorine. So our 0 molar plus 1x equals 2 times 10 to the negative third molar. So we're going to set these equal to one another, and we're going to solve for x. So I've set those two boxes for chlorine equal to one another, and this is essentially 1x equals 2 times 10 to the negative third. So we know x is 2 times 10 to the negative third. Now that I know what x is, I'm going to substitute x back into my ICE chart for the last equilibrium row for the remaining chemical species. So for our reactant, it will be 8.70 times 10 to the negative third molar minus 2 times 10 to the negative third molar. So that's going to give me an answer of 6.70 times 10 to the negative third molar. Repeat the process for our product. It will be 0.298 molar plus 1x. Subbing in our x, we're going to get an equilibrium concentration of 3.00 times 10 to the negative 1 molar. So as a recap here, we set our equilibrium concentrations of chlorine in terms of x equal to the actual equilibrium molarity, and we solve for x. And then we plug that value of x back into our ICE chart so that we can solve for the other equilibrium concentrations of the remaining chemical species in this system. So let's answer the question. They want to know what are the equilibrium concentrations of everything, and then they want us to calculate Kc. So according to my ICE chart, at equilibrium, these are the equilibrium concentrations of all the chemical species. Now to calculate the value of Kc, first start by writing the Kc expression. We know that's products over reactants, using square brackets for concentration. Exponents come from our coefficients from the balance equation. Now you're going to plug in the equilibrium values into that Kc expression. And we get a Kc answer of 8.96 times 10 to the negative 2. Double check your Ks. Remember two things about K. Always positive and doesn't have units.